Okay, should begin. Okay, so we begin today. Today is the last lecture on deep learning and neural network word association. So, what we did in the last class was we did text entailment, and text entailment is really about one piece of text T implying another text which is called hypothesis. Okay. So, many applications like summarization, question answering, information retrieval, machine translation evaluation, these are looked upon as special cases of text entailment. So, this is really very fundamental to natural language processing, and we spent quite an amount of time discussing how to compute the similarity of two texts with different structures, with words, groups of words, parse tree, and so on and so forth. So, this was the material in the last class, and sentiment analysis was planned, but we will do sentiment analysis in today's seminar. So, in this lecture I want to give you two important messages. Okay. One is the method of capturing word association, which is of course very old in natural language processing. And like any other scientific discipline, in natural language processing also we see the reappearance of old ideas in new forms. So, this word association through neural network is, to use a very familiar phrase which is very relevant in France surely, this is old wine in new bottle. So, we would like to capture word association, and we would like to do language modeling. So, we understand the importance and definition of language modeling. The main notion is to capture the probabilities of word sequences. Okay. And how do we learn these probabilities of the words? We apply counting. Okay. So, we count how many times a sequence of words appears in the corpus. So, from this count we obtain the probability of word sequences, and that is understood to be very convenient for many statistical natural language processing, and of course, it all came from speech. So, however, counting actually suffers from data sparsity. If you have a word sequence and any of the word in the sequence does not appear in the corpora, then we know that the probability becomes 0, and we have many different techniques of smoothing, add one, good Turing, Naser knee, all kinds of smoothing techniques exist in statistical NLP. They are pretty old. So, the idea is that can we operate in the continuous space instead of discrete space, okay, where we know that the change of input does not entail a dramatic change in the output. Okay. So, an incremental change in the input has a reasonable change in the output. So, if what is the relevance of these two word sequence probabilities? That means, even if one word is missing from a sequence of words, and this is a small change, okay, in the sequence of words, so why should the probability drastically go from some finite value to 0? Okay. Is there a way we could arrange for this kind of situation? Okay. So, that is one point to work in the continuous space. The other point is how to capture word sequence probability, how to get the word sequence probability when we have the probabilities of a similar sequence of words, semantically similar. So, if you have the sequence dogs bark, and we know the probability of this sequence, cats mew also should be possible to be estimated, because dog and cat, mew and bark, these are similar entities. Okay. So, the capturing of similarity and tolerance to small changes, that is the motivation behind neural network based language modeling, okay, neural network based approach to natural language processing. So, we have only 1.5 hours, and it is impossible to give everything which is going on in deep neural network, but I would like to touch upon some fundamental things and from which one could build later. So, language modeling through neural network, the motivation is to work in a continuous space, okay, and not discrete space. And we know that probability values after all are in continuous space. Okay, it is a set of continuous values in the range 0 to 1. So, as far as the problem requirement is concerned, we are saying nothing new. The methodology has to be in the continuous space. Okay. Now, there are two definite lines of work in neural network based language modeling, okay, two competing lines of work, and other things are all variations of these two lines. One is Hinton's line of work, which is recurrent neural network language modeling. We will spend quite an amount of time on this. And the other line of work is Bengio's, which is feed forward neural network language modeling. Okay. And we would like to look at this also, but I think we will spend more time on the first one. So, let me right in the beginning describe a very commonsensical and obvious point which comes later. If we have this word sequence which is shown on the left box, we have a word sequence, then the probability of this word sequence, okay, can be captured in terms of a set of output elements, okay, output elements, and these probabilities can be obtained in a form which is shown on the right hand side. Okay. So, is it okay? So, this is an entity which is being given different class levels, okay, with different probability values, and the probabilities are being computed by means of an exponential function in the numerator and a normalizing factor in the denominator. This is known as what is called the softmax function, okay, an exponential divided by a normalizing quantity, which is sum of this kind of exponential probabilities. But we talk more about this little later. It is an important module in our discussion. So, we get into this old notion of capturing word association. Now, in terms of NLP layer, we are really coming back to the level of words, but the idea is that a sequence of words would like to get the features of pause tagging, would like to get the features of parsing, and so on and so forth, different information from different layers in different layers of a neural network. Okay. That is the correspondence between a deep neural network and natural language processing layers. Okay. At every layer, we would like to get an abstract feature representation which corresponds to a higher level of language processing. Okay, that is the correspondence. Now, everything goes back to the idea of distributional hypothesis. Okay. This comes in many different forms, and I have here Harris's distributional hypothesis. We group A and B into substitution set whenever A and B have the same or partially same environments. Okay. This is Harris's distributional hypothesis, and we have a few examples here. The trees turn yellow here about the middle of autumn. The trees turn yellow here about the end of October. The first frost comes after the middle of autumn. We start hitting after the end of October. Now, this phrase end of October and middle of autumn. Okay. These two phrases are possibly semantically similar because they appear in the same environment. Okay. Twice they appear in the same environment. The first frost comes after the middle of autumn, and we start hitting after the end of October. So, the first frost we start hitting, trees turn yellow, and so on and so forth. They are similar in their semantics, and therefore, these two phrases are also possibly similar in their properties. So, we make use of n-grams, which tries exploiting the contiguity. So, probability of a sequence of words, the words going from 1 to n, is estimated by a product of n-gram probabilities, okay, after applying chain rule and making use of the Markov assumption. So, this is a method of capturing word association through n-grams and product of n-gram probabilities. Okay, this is a well known thing. Then the Markov assumption says that nothing matters in terms of the probability calculation if we go beyond a window. So, now the bigram probabilities are estimated by the maximum likelihood approach. So, probability of Wi given Wi minus 1 is count of Wi minus 1 W divided by count of Wi minus 1, and this we know is at the heart of language modeling by n-grams, but can get into problems because the counts have to be non-zero. The next significant effort towards word association capturing was latent semantic association, which is a very important milestone in modeling of word sequences and word associations. So, the idea is this, that it is a theory and method for extracting and representing word in context. Okay. So, the most important element here is word in context, and we have to make use of statistical computation applied to large corpus of text, and here we see the similarity with deep learning methods these days. We again have large corpus of text, and we have again concern with word in context. Okay. So, you can see that the goal has remained same since 1980s or 70s, I would say 80s, I would say. The goal has remained same. To capture word association, only the technique has changed. Okay. And also the score that is used for these word associations are obtained by a black box, which is a neural network. That is the main idea. So, now the underlying idea is that we would like to aggregate all the contexts in which a given word does and does not appear. Okay. So, we would like to provide a set of mutual constraints that largely determine the similarity of meaning of words and sets of words to each other. Okay. So, we would like to provide the association between a word and its contexts and the mutual similarity between a set of words, the internal similarity. So, and we would like to provide a set of mutual constraints. So, when we have a technique like neural network, the mutual constraints come because of the weight connections, okay, connections and their weightages in the neural network. In LSA, we will see that we need a set of matrices and their eigenvalues which capture this association. So, in this whole environment, the text is a point in the semantic space. Okay. Words and any set of these words such as sentence, paragraph, essay, anything taken from the original corpus or from a new corpus they are represented as points in a very high dimensional semantic space. Okay. So, this point is captured by means of what is called the singular value decomposition. Suppose X is a word versus context matrix, then we can represent X by a product of three matrices X, S and D, where X is of dimension T into D. T is the term, set of terms, number of terms. D is the dimension of the contexts, okay, the number of contexts. Then T0 is T into M. M is the hidden matrix which is found by singular value decomposition. A is of rank M, and S0 is M cross M, D0 is M cross D. Okay. So, it is possible to break a term versus context matrix. Okay. We are not going into a lot of details here, by singular value decomposition into this kind of three matrices. So, the mathematics is as follows. T0 consists of left singular vectors, that is the m eigenvectors of A transpose as columns. D0 consists of right singular vectors, that is the m eigenvectors of A transpose A, and S0 is a diagonal matrix of m singular values, that is the positive square roots of the eigenvalues of AT. So, here is an example. Suppose X is in this form, where there are 5 words. Okay, there are 5 words in the rows, and for the moment the number of words and the number of contexts are same. The rows are the contexts. Context means pieces of text in which these words appear. Okay. So, these numbers here are counts of those words in those contexts. Okay. So, this is simply a term frequency versus context matrix. Okay. So, now can we say that each word is represented by a vector of frequencies? Okay. So, if I take any word and take any row, can we say that this row is a representation for that word? Okay. So, we might say this, but the problem is that these values are discrete. Okay. There are zeros and count values. It does not explore the semantics of the word as finely as it should. Okay. For example, the word cat and dog appearing in these rows, okay, there is nothing in those vectors to say that cat and dog are really semantically similar. Okay. So, can we do better? Now, what is the intuition? How can we do better? Okay. How can we do better? We can do better if we see that the context dimensions, okay, the columns here, some of those columns can be merged together to create a new dimension. Okay. To create a new dimension. So, in which case, since the number of dimensions becomes smaller, the similarity between two words becomes more apparent because of this merging of dimensions. Okay. So, let us see how it happens. So, first of all, we take X transpose, that will produce a square matrix. Okay. Now, we get the eigenvalues of this square matrix. If we compute, we will get these eigenvalues, and corresponding eigenvectors for these eigenvalues are also shown in this matrix. Okay. So, complementarily, we also have to take XTX, okay, and this is turning out to be a set of numbers again in another matrix. XTX has the same eigenvalues, and the corresponding eigenvectors are the rows of the D transpose. Okay. So, all these are possibly very well known things, and not going to the details, but the computation is quite obvious. Then the diagonal matrix of the positive square roots of eigenvalues of A transpose T or AAT are these, okay. And the three matrices which come out from the singular value decomposition are as shown here. Okay. Yeah.
So why do you have everywhere square matrices? Normally in LSA you don't.
No, you don't. You don't.
And here to have always 5 by 5, which makes it
yeah.
a bit puzzling, because eigenvalues are not singular values. That's two different concepts.
No. So X is
vectors are just for square matrices.
right. No, so as I said in the beginning, this X matrix was a hypothetical matrix, and for convenience was chosen to be a square matrix. Actually, the words and the number of contexts need not be same. The number of columns can be, and SVD can apply to any rectangular matrix. If we have to work with only square matrix, then maybe principal component analysis is better. Okay. So the idea behind all this is that we can choose the significant eigenvalues, okay, and combine dimensions on the column to have a reduced size feature vector for each word. Okay. So the effect of all this is to finally combine the columns. Okay. And if we work with a column by word matrix, then the effect will be to combine words to capture the similarity of different contexts. So this has been very frequently applied in case of information retrieval, where the technique is also known as latent semantic indexing. So the further steps are, we arrange the singular values in S in their descending order. Correspondingly, we also swap the columns of T0 and rows of D0, and then there is this dimensionality reduction step, where we retain only those dimensions which are corresponding to the highest eigenvalues. Okay. So what we have achieved through this is that we have represented X by a different matrix. Okay. Again, everything is shown in this matrix. This really does not show the dimensionality reduction, but we can drop a few columns from this matrix and obtain the feature vectors of the words through this technique. Okay. So this is a well known technique called LSA, and the effect of this is to get a set of numbers which are on the rows to give the feature vectors of words. Okay. Any question or any comment on this? The whole point is that we have merged dimensions, that is, we have merged columns or rows to get a representation for an element in the matrix. And this merging of columns happens with a weightage. Okay. So to given two columns C1 and C2, we get a new column D, which is equal to W1 C1 plus W2 C2 with appropriate weightages learned from this technique. Okay. So in binary vector representation, we get a Boolean vector for a word, where this Boolean vector indicates whether the word is present in a context or not. In the term frequency based representation, we get a vector for the word which shows how many times this word appears in these contexts. Okay. Now in SVD, we get a representation for the word which says, okay, what is the representation of the word in terms of different contexts when these contexts are properly weighted and merged. This is the idea. Okay. All the maths can follow later. Okay. Any question, comment? Okay. Now, we would like to go from LSA to the neural word vector, okay, which is the main concern of today's lecture. So, given these words W0, W1 up to Wn plus 1, we would like to get the representations of the words Wi. Okay. And in LSA, only contexts are captured. What about other properties of the words? Okay. Words have their morphological, syntactic and semantic properties. Dog and cat have stronger semantic similarity than dog and house, for example. So, animacy is an important property. LSA does not capture this, isn't it? So, there is nothing in the algorithm or the representation where we see that the property of the word is accounted for. So, can the deep neural network based modeling do something about it? Okay. But how could that happen? Okay. After all, we are working with corpus, and in the pure deep neural network based model, the whole corpus is unannotated. Okay. How can the semantic property come out? How is it possible? Yeah.
Actually, I think nowadays there are extensions of the idea of LSA using tensors to update
Yeah.
other information.
Yeah. Of course, but it is all association ultimately. Yes. But intuitively, what do you feel? How can we capture, let's say, animacy? How can we capture animacy if there is no tag called animate in the corpus? How can it happen?
From the context, if you analyze a very large amount of data, you get some information.
Yes, but what exactly happens? So, let me say that the following thing happens, that there is a level of processing where what will happen is that dog, cat, tiger, lion, they would all come together. Okay? House, table, chair, curtain, all this will come together. Okay? One neural network will simply do this. Okay, very trivially. One neural network will simply do this. It will take the representation of words like cat, tiger, lion, etc., put them together, and house, furniture, table, etc., in another. Now, this, the output of this network will be fed to another neural network, okay? And the second neural network already has animacy, inanimacy separated. You see that? Okay, that is the main idea, and this is the main point about deep neural network. We stack neural networks one after the other, where the output of each neural network, each layer, is an input to the next layer, and the output is a form of clustering where the words are put together because of their inherent semantic property. This is the main idea about deep neural network. Okay. Otherwise, why should dog and cat be together? There is nothing in the corpus. It is all unsupervised learning. Why should they be together? They come together because of their distributional property, of course. And the moment they come together, we say that they have something common to them. That something happens to be animacy, which is a label given later. Okay? And if this cluster is an input to the next layer, it already has the feature of animacy to it, available to it. That is the idea. Okay? Clear? This is the intuition.
There's a question. You
Yeah.
use the word layer.
Yeah.
Usually in semantic, in neural nets,
Yeah.
one or two or three hidden layers, and those are called the layers.
Yes.
Between the input and output. But here you seem to use the word layer as the input vector or output vector, which is the input vector of the next. So it's not the same, huh?
No, these are two different architectures. I'll discuss both of them.
No, but
Okay.
I mean, what is a layer traditionally in neural net?
Yeah.
Has not Hopfield net, huh?
No. Feed-forward network.
Okay, feed forward, etc.
Yeah.
This has one input layer, output layer, but the intermediate layers are not communicated to the other.
Right.
They are not combined in this way only.
Yeah.
Output of one is input of the next.
Yeah, so I'm coming to that, but just to answer your question in 2 minutes, what is done in deep belief networks is that this kind of neural networks with only 2 layers, okay, one of them is called hidden, the other is called output. They are all put together. The final layer is what is a soft max layer, and then then a backpropagation algorithm is run on this stack of neural networks, which is what I am coming to. Okay. So all this is, as you say, all this is old knowledge, but everything put together in a different way, I would say. Okay. So the context is represented in many different ways. I show here 3 representations. The first representation is Boolean, presence absence. Second representation is counts, and third representation is normalized counts. So this third representation is important for us. If you take the counts and divide them and you normalize them, then you see we have an interesting point emerging. A context has become a probability distribution. Okay, a context has become a probability distribution. Equivalently, a word has become a probability distribution. It is a set of numbers whose summation is equal to 1. Okay, and now we are at a very advantageous position. The moment I have a probability distribution, okay, I have all the techniques of probability available to me. In particular, I can compute the distance of a distribution from another distribution by what is called relative entropy. Okay, and that relative entropy becomes a figure of merit for me to do learning of parameters. Okay, that's the idea. Now we get into a bit of neural network, but very quickly, so that we can come to our main discussion. I would like to cover some milestones which have led to today's excitement in deep learning. Now, the first point is that the brain is composed of many different regions and layers. There is this forebrain, which is the seat of language ability, mathematical ability, cognition, emotion, and so on and so forth. This is called beginner's brain map. Then there is midbrain, whose job is mainly information routing and involuntary controls. The cerebellum is for motor control. Hindbrain is the control of breathing, heartbeat, and blood circulation. And spinal cord is for reflexes, information highways between body and brain. So we would like to, I mean, this is a bit of digression. See that things which are very critical to our survival are in the hindbrain, control of breathing, heartbeat, blood circulation. Anything going wrong there, our existence is jeopardized. Okay? And it is also interesting to note that nature has taken a lot of care to put that part of the brain at the back, okay, so that it is very safely stored in our bodily functions, in our anatomy. Okay. So then we also know how neurons perform. They are composed of what are called dendrites, and there is this cell body, which is essentially a solution of sodium and potassium. And then there are axons which generate and relay the action potential. So, inside the neuron there is complete neurological evidence now that a summation of weighted input of signals happens inside the neuron. This is known, and this has given rise to what is called the perceptron model. Okay. So, a perceptron is a computing element with input lines having associated weights and the cell having a threshold value. So, the output y becomes 1 whenever this weighted sum or the dot product of the weight and the input exceeds the threshold. So, this is the first building block in our neural network, and we know that y is equal to 1 if sigma wi xi is greater than theta, otherwise it is 0. So, this produces a step function, but we know that this kind of input output behavior is not very good because we cannot take derivative, for example, which is important in many of our modeling tasks. The perceptron training algorithm is very simple. We start with a random value of the weight values. We test if w dot xi for any input vector is greater than 0. If it succeeds for all inputs, then we return that particular w as the weight value. Otherwise, we modify the weight as previous weight plus the vector that failed. Okay. So, this is a very, very simple learning algorithm. It is in the form of a reward and punishment, we can say. And the perceptron convergence theorem says that whatever be the initial choice of weights and whatever be the vector chosen for testing, perceptron training algorithm always converges if the vectors are from a linearly separable function. So, this is known. Now, the thing which is of great interest in the community is really the feed forward neural network, and the algorithm which is used for training such a network is backpropagation. So, now we take a very simple example, and this is important because it says something about deep neural network and neural network based learning. So, we know that XOR cannot be computed by a single perceptron. Okay, it is not linearly separable. So, this is this becomes computable if we have a hidden layer. Okay. So, this is the hidden layer inside. The output is the final neuron. The two boxes with x1 bar x2 and x1 x2 bar are the neurons which are hidden. Okay. They do not receive any input or they do not give any output, but they are critical to the computation. Okay. And this is a very important point. I have purposefully put this here because it shows the importance of discovering hidden features. Okay. It is really discovering hidden features in the problem. In the computation of x1 and x2, there is a hidden computation of x1 bar x2 plus x1 x2 bar, or x1 plus x2 multiplied by x1 bar x2 bar. Okay. These are the two ways in which the XOR is computed, and the wonderful thing is that if I have this architecture and if we run a learning algorithm on this, this hidden computation is discovered by the hidden layer neurons. Okay. As if they have found out, these neurons have found out on their own that I have to compute XOR, I have to go through this intermediate computation of x1 bar x2 and x1 x2 bar. This is indeed the principle of any kind of neural network modeling. We discover hidden computations. Okay. So, what is done in this is that we apply gradient descent technique, and suppose E is the error at the output layer. This kind of error functions are also called loss functions. Okay. So, these loss functions come again and again in any kind of machine learning situation. So, Ti is the target output, Oi is the observed output, and I is the index which goes over all the neurons in the outermost layer, and J is the index which is going over all the P patterns. Okay. And if the problem is XOR, then p is equal to 4 and n is equal to 1. There are 4 patterns and there is only a single neuron at the output layer. Okay.
What are the 4 patterns?
For XOR there are 4. So 0 0 0 1
Okay.
1 0 1 1. Yep. And the output is either 1 or 0. Okay. So when we try to minimize this error and we adjust the parameters to minimize that error, then we have got a network which has learned how to compute that mapping. And it has not only learned how to compute that mapping, it has also discovered the hidden computation needed for this mapping. Okay. So for example, given a sentence, if you would like to compute the sentiment of that sentence, okay, by a neural network, then the intermediate layers would produce a hidden computation to detect that sentiment analysis, to detect that sentiment. And those hidden computations, what are they? Okay. Those hidden computations can be, maybe we are discovering the part of speech of the words indirectly by clustering them. We are discovering the semantic properties like animacy, again by grouping them together. So all this is automatically happening in the hidden layers. Now this is well known, this is since the 1980s. What has happened in the recent times? What is the contribution of deep neural network here? Okay. This is known. What is the difference is the difference is the stacking of neural networks. Okay. In case of feed-forward network with backpropagation, which is this feed-forward network with backpropagation, this is the outermost layer, the right layer is the outermost layer, this is the input layer. I have no control. Okay. I have no control. These hidden layer neurons, they compute, they discover that intermediate computations have to be done, but I have no control on them. Okay. I can control only the number of neurons and the number of layers. After that, what they do is not in my control. So what today's deep learning does is that it takes this, okay, and runs a recursive Boltzmann function on this, which I am going to do, then takes this output, feeds it into another layer, looking upon this as the hidden layer and the next layer as the visible layer, then trains it, gets the features here, produces this as the hidden layer, next layer as the visible layer, and this kind of stacking goes on. Okay. So this is the main difference between old feed-forward backpropagation network and stacked neural network with a softmax layer at the output. This is the difference. Okay.
And the reason why this is done is because of computational limits of this free connected approach, or there are other reasons?
You want to control what is happening in the hidden layers. You want to control it. So we know the general backpropagation rule. Okay. Again, the maths is quite easy. We simply take the derivative and apply lots of partial derivatives and their chaining to get this expression that the change in weight. Okay, let's note this expression. The change in weight is eta, which is called the learning rate. Okay, learning rate is again applied in today's deep neural network. Something called delta J, okay, which is depicted here. OI is the input. So this is the weight change rule for a particular weight in the neural network, a particular weight in the neural network, Wji, and that is changed by an amount which is a function of OI, the output of the ith neuron, and a quantity called delta J in the jth neuron. Okay. And that value is equal to Tj into Oj, departure from the target behavior, into Oj into 1 minus Oj, which is at the outermost layer. But for hidden layers, since we do not know the output values there. This value becomes Oj into 1 minus Oj, which is fine, into Wkj delta k, which is a recursive quantity back propagated from the subsequent layer. Okay. So, the way the computation proceeds is as follows. We give an input here, then since the weights have been initialized already and since the input output functions are known for all these boxes, we know the actual output here. From this we know the actual output here. Now, this is a supervised setting. So, I know the target value here. I already know the target value. So, I know the amount of error which is committed here. This error is multiplied by the weights here, okay, and passed on to these neurons here. Those errors are again multiplied by the weights here and passed on to the neurons here. Okay. And all these weights are changed according to the error value and the output value here. This is the main idea. So, forward propagation of the signals and backward propagation of the error. Okay. So, therefore, we get this particular formulation, and this is the general backpropagation rule. So, now I come to the restricted Boltzmann machine, and this is a bit mathematical. I would like to spend some time on the mathematics part here, okay, and then move on to other things. So, this has been a very important module for deep neural network. Let us see how the neural network looks. So, we have only 2 layers, and this is a very simple machine shown here, where we have V1 to Vm as the input layer. This is called the visible layer, and hidden layer neurons are called H1 to Hn. Okay. There is complete connection between the 2 layers, but no connection within the layer. Okay. So, there is layer to layer connection, but no connection within the layer. So, this is fully connected. That means every neuron in the H layer is connected to all neurons in the V layer. And the parameters here are weights between the 2 layers, and they are bidirectional and symmetric. Okay. That is an requirement for these restricted Boltzmann machines. There are biases on the visible units. So, B1, B2 up to Bm, there are m visible units. Similarly, there are biases on the hidden units C1, C2 up to Cn. So, visible and hidden units. Now, there is an important quantity which is used for the computation of such networks. This is called the energy. Now, the H neurons in the hidden layers, they have a state capital H. Okay. These are the values on those neurons. And the V neurons in the visible layer, they have the state V. So, the whole neural network has a state which is described by HV. Okay. So, the values of these H neurons and the V neurons describe the state of the network. The energy of this neural network is defined as V transpose WH minus B transpose V minus C transpose H, which is nothing but the pairwise product of Vi and Hj. Okay. The activations in the visible layer multiplied by activation in the hidden layer and multiplied by the connecting weight. So, I equal to 1 to m, j equal to 1 to n, Wij, Vi, Hj. This is one expression, and minus Bi, Vi minus Cj, Hj. This is called the energy expression for the neural network. Okay. So, the energy is surely a function of the state. State is h and v together. So now let us relate it to a particular problem, some problem in natural language processing. Okay, that's when we will understand the relevance of this machine. Suppose we denote a sentence by a set of words w0, w1 up to wn plus 1. The input sentence is a set of words which is pause tagged with noun or not noun. Okay. Now, we would like to understand if each noun there is a named entity or not.
Sorry,
Yeah.
so the first tag is the output, not the input.
No,
Tag information.
post tag is the input. Input, yes. So, we are given a sequence of words and we want to do named entity identification, not recognition. So, we want to identify each word as a name or not a name.
Name entity or name?
Named entity, named entity, yes. So, for example, if the sentence is Taj Mahal is the most visited site in India, then there are two named entities, India and Taj Mahal. So, the output will be 1 and 1 here, everything else is 0. Okay. And the whole input is pause tagged with noun or non-noun. So, input is also a 1 0 vector. So, the input is 1 0 0 0 0 1 0 1, and out of them only first and last words are 1 1. Okay. This is the problem. Then we will have a restricted Boltzmann machine which after its computation will settle at a state, okay, if it works properly, where all these visible units will have ones and zeros, and the hidden units, sorry, visible units are ones and zeros, hidden units also will have ones and zeros. At the hidden layer, okay, we will get the named entity information. At the visible layer, we have the noun, non-noun information, okay, after the computation. And why should it settle to this state? That is because of this kind of probabilistic computation. Okay. Probability that aj is equal to 1 given v is a function of the net input, of course, which is 1 by 1 plus e to the power minus net j, and net j is equal to wji vi minus cj. Okay. Similarly, for the visible neurons. So, each neuron has this particular property, it is a logistic regression function. Okay. Probability of a neuron being 1 in a state of 1 given all the neurons in the other layer is equal to this quantity. Okay. So, how does the computation proceed? We impress the input pattern onto the visible layer and let the hidden layer be anything, h layer be anything. Then there is a symmetric connection from layer to layer. The neural network will begin to compute in what is called an asynchronous mode. Okay. It is a restricted Boltzmann machine, and eventually will settle down to a minimum energy state where we hope that this particular pattern will emerge in the hidden layer. Okay. Is it clear? And this is the probability of a neuron being in 1, which is a function of the net input passed through a logistic regression function. Okay. So, then the probability of a state of the network is given by the energy of the state. Probability of the state of a neuron is given by a sigmoid. The weight and biases should be adjusted such that the desired HB combination is stabilized in the network. Okay. Now, there is a very, very key point, okay, which is really the theory of the RBM, which is this way: establishing a correspondence between the macro probability and the micro probability. Okay. The micro probability is the probability of a neuron being in the state 1 or 0. Macro probability is the probability of the whole neural network being in a state. Okay. So, the question we are asking is that if this is the energy of the whole network, this is the probability of the whole network being in a state, okay, and if each individual neuron has the probability function given by logistic regression, how come are these two consistent? Okay. Do we get this probability of the whole network in this form if the probability of each neuron's activation follows logistic regression? Are these two consistent with each other? Okay. So, this question is very similar to a question in Newtonian mechanics. Okay. There is an equivalent question in Newtonian mechanics. The kinetic energy of a system is half mv square, okay, half mv square, and the Newton's second law says that the force is proportional to rate of change of momentum. Okay. Energy expression and the force expression, are they consistent with each other? Okay. The energy expression has to be half mv square if the force equation is derivative of momentum, first derivative of momentum. So, the energy the probability of the macro probability, the probability of the state of the whole network has to be this if the probability of firing of a neuron follows the logistic regression. These two are consistent with each other. So, this is the proof I would like to show now. Okay. Oh. Okay. So, we would like to establish a correspondence between macro and micro probability. So, just bear with me for a bit of maths because this is important. So, probability of the whole state of the neural network is given by e to the power minus energy corresponding to this state divided by a normalizing factor, which is nothing but the e to the power the energy for all possible state combinations. Okay. We have 2 sigmas here. So, the probability of the state is given by this. From this probability, we would like to deduce that the probability of the neuron, of one neuron firing, has to be a logistic regression. So, probability of hi equal to 1 given V is 1 by 1 plus e to the power minus net I, and net I is equal to sigma w j I v j plus c I. Okay. So, we would like to show that these two are consistent. So, forward probability is this: probability of the state implies probability of the neuron. So, energy is equal to sigma I equal to 1 to n, j equal to 1 to m, w j I h I v j. This is the activation coming from one neuron to all the neurons in the other layer and vice versa, minus the activation of the visible layer neuron multiplied by the threshold minus activation of hidden layer multiplied by the threshold. Now, probability of any state H given V is joint probability of H and V divided by probability of V by the law of probability. Okay. And this of course is PHV, and here I can apply marginalization and I get probability of H hat V. Okay. So, which is equal to e to the power minus E H V divided by Z, the normalizing factor by definition, and this also has to be e to the power minus E H hat V, H is the variable here, H hat is the variable here, divided by the normalizing constant Z. Okay. And therefore, this is equal to e to the power minus E H V divided by e to the power minus C H hat V, where H hat varies over all possible states. Okay. What is our goal? Our goal is to prove that this probability will be equal to, will give rise to the probability of the firing of a neuron for consistency. So, now we assume alpha I v is equal to sigma of j equal to 1 to m w j I v j plus C L, okay, j L v j. So, this is for a for the visible layer. So, now E h v, or this should be minus. So, E h v is equal to beta L h minus L v minus h L into alpha L v. Okay. So, okay, sorry. So, P h L equal to 1, we are concentrating on a particular neuron in the hidden layer given the vector v in the visible layer. E is equal to P h L equal to 1 and all possible states of h, okay, without L augmented with v. Okay. And this becomes now a joint probability with h L equal to 1 and leaving out only h L considering all other possible neurons, which is equal to this expression. Okay. P h L equal to 1 and v divided by sigma over all possible h L's and h minus L and v. Okay. So, we are trying to get an expression for h L equal, probability of h L equal to 1. So, if we carry on in this way, we find that the probability of firing of a neuron in the hidden layer is equal to 1 by 1 plus e to the power minus alpha L v, where alpha L v is nothing but the activation in the particular neuron. Activation in the particular. So, some amount of algebra brings us to the conclusion that the probability of the firing of a neuron has to be this, okay, if the probability of a state is in terms of the energy expression. And the probability of a neuron implying the probability of the state, that also can be quite easily shown. Probability of h L equal to 1 given v is 1 by 1 plus e to the power alpha L v by definition. Now, e to the power minus alpha L v can multiply both denominator and numerator, and then we can also multiply this by e to the power beta h minus L v, okay, both numerator and denominator multiplied by this way, and this gives rise to a quantity which is shown in the third step. So, from this probability of h, capital H given v is I equal to 1 to n p h I equal to 1 given v. This product expression is fine because there is no internal connection in the hidden layer. Okay. Similarly, there is no internal connection in the visible layer. The hidden layer is affected only by the visible layer and vice versa. So, this product is okay. Okay. So, then because the probability of firing of a neuron is known, then we can apply this algebra and finally arrive at the conclusion that probability of h given v has this form. Okay. The joint probability of the hidden layer and the visible layer state comes out to be equal to e to the power minus energy of the neuron at states h and v divided by the normalizing factor. Okay. So, the purpose of these maths was to show that logistic regression is critical for this kind of functioning of recursive restricted Boltzmann machines, okay, and these two are consistent with each other. So, now from this we do not have time to go through all these derivations, but this is again quite easy algebraical manipulation. Probability of a particular visible state V is 1 by z sigma e to the power minus e v h, where h varies over all possible hidden states. Okay. So, probability of a visible state is given by this equation. Now, if we take log of PV and take its derivative, then the derivative comes out to be in the form of expectations, okay, expectations of these quantities when the V is given fixed, and the expectation over the whole model. Okay. This is coming because of the normalizing factor, and the expectation of course is also quite easy to get from the definition of probability into value. Then the change in weight is equal to learning rate into difference in expectation with respect to data and difference in expectation and the expectation with respect to the model. This is quite similar to what we get in the entropy based models. Okay. And the probability of a hidden neuron firing is given in terms of this quantity. Okay. So, probability of a hidden neuron firing is in terms of the quantities in the visible layer. Probability of visible layer neuron firing is again in terms of what is happening in the hidden layer. Okay. So, an expectation maximization is involved in these two equations 1 and 4. That means there is an iterative algorithm, okay, which runs between the hidden layer and the visible layer obeying these equations, and the weight change is affected by means of difference of expectations, and then we hope that the neural network has learned the pattern.
Sorry, but here only the weights are changing. What about the biases?
Biases are also captured here, really.
Where?
So, so this is a standard trick, right, in neural network, that we introduce a fictitious neuron, okay, whose value is fixed at -1, and the biases are weights for those. So,
But just in the slide that is just after this one,
yeah,
just 49, you have a matrix of weights, but you have also two vectors for the biases.
yes, yes.
My question is how these biases are updated during the training.
Okay. So, now if I have a Vm plus 1, okay, if I have a Vm plus 1 which is fixed at -1, the activation value is always fixed at -1, and it connects to all the hidden layer neurons. Those weight values are C1, C2, etc. Then effectively what I have is that the biases have become weights connected from a -1 neuron to all the neurons here, and vice versa. Okay. So, those weight values also can be changed by the same equation. So, one of the VIs will be Vm plus 1, which is -1, okay, and one of the H's will be Hn plus 1, which is again -1. So, what I am saying is that the expectation, these vectors, okay, will be augmented by another -1, which is fixed. So, it is possible to do it that way. Okay. So, then we have what are called stacked restricted Boltzmann machines. These are also called deep belief networks. So, So there is these visible units or the input vectors. Then there are 500 hidden units, again 500 hidden units, and so on and so forth. And finally, there are these class level units. Given input X, train an RBM to learn H1. Use H1 as input to train another RBM stacked above to get H2. Similarly, get H3. Now the weights connecting layers learn some kind of hierarchical information. Yeah, just a minute. But they need to be fine tuned for the given task. Now we use the usual backpropagation algorithm to train the entire network. Yeah.
I don't know if you are going to talk about the gradient vanishing problem, how it comes and how it is solved.
Which problem?
Gradient vanishing problem.
Gradient vanishing
Yeah. No, it's not the term.
or gradient descent?
No, gradient. I think it's a. Well, I'm not. I don't know much about it, but it's, so when you backpropagate the gradient as you apply a step,
Yeah.
then the propagation will vanish quite soon if you apply deep neural network, right?
Okay. I see. So you're saying that the quantity becomes very small?
Yeah.
Okay.
Perhaps the term is not exact, but it's a common problem, right? And how people avoid it, because I don't know.
Yeah, I don't know, but what I see is that I do not know about deep neural network really, but what happens in the neural network is normally you have at most 2 hidden layer neurons. Okay, at most 2 hidden layer neurons, and it has been found that in most cases 1 hidden layer is good enough. So they probably do not face this particular problem of vanishing gradient descent. So I need to really look it up. I understand the problem. So since there are many layers during backpropagation, you keep on multiplying small quantities, and this can become a problem. I need to look it up. No, I am not going to discuss that. Okay, so I'm going to throw some terms now. So there are these important techniques for training the data. There is what is called hierarchical softmax, which is nothing but stacking of restricted Boltzmann machines. There is something called noise contrastive estimation, negative sampling, subsampling. These are used in the context of restricted Boltzmann machines.
Can I ask a question?
Yeah.
Just a slide before.
This one?
The one with the different.
Yeah.
This one.
Yeah.
So you start from the visible unit, the input vectors.
Yeah.
You say that the first step is to train the RBM to learn the
Right.
H1.
Right.
But then what is the targeted output? I mean H1, so because there is no annotation here.
Yeah.
The annotation is just eventually at the end.
Yeah.
So what is the target?
The target is really a set of class levels. Okay. So how let's see. So suppose I have this as a set of input words, or maybe just a single word here. Okay. And at the final layer, I would like to obtain the probability of that word being a noun, verb, adjective, adverb, okay, appearing in different neurons. Okay. And it should be such that those probabilities sum to 1. Of course, they have to sum to 1, and they are computed by means of the sigmoid input-output function. Okay. So it is a set of probabilities, and since they are computed through sigmoid input-output functions, they are also called softmax layer. This is actually in the form of an exponential divided by a normalizing factor. Okay. So the output is a set of classes with their probability values.
Yes, but the output of this block up. But when you do the first step, which is given input X, train the RBM to learn H1,
Yes.
I actually do this stack by stack.
Right.
So what is the output of the stack here?
The first
Yes, yes.
first level of output.
Because I don't have no truth for that. It's hidden, right?
Right, right. So that that is an abstract feature. So there is a set of H neurons here, okay, and the outputs are a set of vectors. The output is a vector, okay, and the meaning of that vector, what it represents, is not really clear. Okay.
Yes, but to train, because this is my target when I do the first step.
Hmm.
So where does it come from? It comes from because with this first step is just we have input, which is something visible,
Yes.
and we have output, which is something hidden, right?
Okay.
And we want to train this.
Hmm.
But how do we fix the values of this output that is hidden?
You don't fix it. You don't
Yes,
fix
but
it.
where does it come from in that case?
So if
You
I
learn it.
yeah, so if I take the, let's say, the named entity identification problem, okay, I have a set of ones and zeros input here,
Yes.
which is simply a vector saying if the word is noun or not noun, and in the output layer I have name or not name, okay. In the maybe the next layer is producing what should I say so okay, ones and zeros is not so next layer maybe produces if the input layer is only words, the next layer only produces the part of speech, okay. The next layer produces the word groupings, okay, all the chunks, for example. The next layer maybe produces the parse, the next layer produces the named entities maybe. So, yeah.
But if you have no fixed level between each layer, what is the energy you try to optimize when you do training?
Sorry, come again.
If you don't have a level at the output of the first layer,
Yeah.
what is the energy you try to minimize to train the first neural net?
No, so see, this network is a fully connected network and bidirectional. It's bidirectional. So this is a network which tries to attain a stable state automatically. It is the property of the network to get into a stable state, and that stable state is a minimum energy state. You do not do anything. The network stabilizes to that state.
So is it correct to say that since at the output just something is fixed because this is a target,
Yeah.
there is with this all full connection something is actually a consequence of this output at the output of the first block,
Yeah.
and actually when we do the first step we actually train the way to predict this first block.
Hmm.
That is a consequence of the fixed
Yeah.
output. This is
Yeah.
is this correct?
This happens when we finally apply a backpropagation. Okay. Finally, we apply a backpropagation to fine tune all the weights after we have run these RBM algorithms.
Yes. So fine tuning, I get what it is because this is really supervised. We have this
Yeah.
output.
Yeah.
But the previous step, I don't really get it. But maybe we can discuss this.
Yeah. But the previous state, previous state is not really previous stage is not really different from what happens for hidden layers in the normal neural network also. You really do not know what is happening at the hidden layers. You only hope that by this kind of staging, okay, we are hoping to get the next level of NLP information which this input can produce, and essentially this is clustering. Yeah, and you really do not optimize energy. You cannot do anything. I mean, there is a bidirectional neural network connection, and it is a form of Hopfield network, recurrent network. And whatever you impress here, the network by its property will try to get to a stage of stability. It can of course be a local minimum, but that's what it will. Okay, so now very quickly, these kind of problems have been attempted. Analogy finding. So Germany is to Berlin, what is France is to what? So find a vector x such that vector x is closest to vector of Berlin minus vector of Germany plus vector of France, and this will give rise to Paris. Okay, this is seen in the literature again and again, and these things have become very popular now. And another association problem is the 4 closest result. What is the currency of Czechoslovakia? Okay, what is the currency of Czechoslovakia? So, from the corpus, because of deep neural network, you get this list of 4 currencies: koruna, Czech crown, Polish zloty, and CTK, etc., etc. I don't know which one is the correct answer. Vietnam capital?
It's zloty, not zloty.
Okay, zloty. And for Vietnam, the capital is what? Hanoi, I suppose. Okay, so that comes out to be the top result.
And Czech is wrong.
Yeah.
CZ and then CH.
So yeah, that should be that. It is wrong. Yeah. German Airlines, Lufthansa comes out to be the right answer, top one. River in Russia, Volga should have been the top answer, I suppose. French actress, I don't know which is the right answer here. Okay. Okay. So this kind of problems have been attempted, and the question is, will this deep neural network based approach replace IBM Watson, which is heavily dependent on NLP tools and resources? Okay. So these kind of questions are answered. So there is this word2vec tool which Google has made freely available. The link is this word2vec, and there is a Python package associated with this. For this source code is open, so the algorithm one can make use of, and for any language one can create word vectors.
But this one is only for English, right?
This is only for English. So we have taken the source code and tried to create word vectors for many Indian languages. They are useful. These are the references. So now at the end, I would like to say the following. This is the summary of the lectures and their topics. In the first lecture, we had introduction and pause tagging, and for each there is one message I have put down. Okay. So in the first lecture, the most important message is HMM based generative model of part of speech tagging. In the second lecture, it was expectation maximization. The main important message is the 2-coin problem. It illustrates expectation maximization very well. In the third lecture, it was statistical machine translation. The main message is expectation maximization based word alignment. The whole statistical MT is from that. Fourth lecture was on named entity and multi-words, and the main message there is feature aggregation with entropy. Okay, how do you combine features through an entropy model? Fifth lecture was on parsing. The most interesting point there was the correspondence between hidden Markov model and probabilistic context-free grammar. These two are very equivalent. Sixth lecture was on lexical resource and words and disambiguation. There the most important point is the role of WordNet in words and disambiguation. Okay, the whole words and disambiguation has become possible because of WordNet. Seventh lecture was on text entailment, and the most important point there is how text similarity is computed. The last lecture is today, deep learning, and the main message there is word sequence probabilities in the continuous space. Okay. And we started with this statement that empirical natural language processing is really probability and linguistics. It is a combination of these two. Hopefully some of these things have come out in the lectures. Now the whole point is, if for a natural language phenomenon we cannot give a rule, then learn that pattern from the data. That is whole of EMNLP. If we cannot give a rule, learn that pattern from the data. Okay. For example, we cannot say several thanks. There is no reason why. Okay. Therefore, we have to say many thanks, and many thanks to you for coming. Okay.